So to start this problem, I knew that this would be a supervised learning task because of the nature of the labeled data. The data that we're given has a specific output, and I further knew this would become a regression modeling problem because we were trying to get a predicted value output, being the net hourly electrical energy output. So I first started by examining the data and plotting all the features against the predicted the target value, PE. I noticed from the start that V and AT had strong correlated relationships against PE. AT looks like it had a negative linear correlation, and that V had a negative logarithmic correlation. And I also thought that AP had a positive correlation, positive linear correlation, and I honestly did not think that RH had much of a correlation, like a vague positive linear correlation, when I first looked at the data. So to evaluate how these models would perform, I decided to use the mean squared error metric. And the reason is because we want generalized predictions and we want to throw away outliers. So we want it to not throw away but penalize outliers. And I do believe that large errors are more critical than smaller errors, so that's what we want to look out for and want to reduce in evaluating the different models and comparing them amongst each other. Okay, so to determine which models I was going to use, I started with a simple multilinear model to do my evaluation on. And then after that, I decided that I would try feature selection by getting rid of RH and see if my hunch was correct in reducing the mean squared error. And then finally, the last model that I wanted to evaluate was a transformation on the multilinear model by putting a logarithmic transformation on V. So in my code, what I did to do all of these model comparisons was I first split the training set and test set, so by 80-20, and then I decided to apply a cross-validation, 5-fold cross-validation to further split the training set to 80-20 once more for the validation. So in the end, the split was 64% of training data, 16% of validation data, and 20% of test data. So I started with the multiple linear regression, and then after that I decided to apply the multiple linear regression but with feature selection, so without the RH feature. And then I also applied the same path, the cross-validation score. This was applied to every single model with a log transformation on V and include every single feature in that multilinear model. Okay, so I will go ahead and demo the output values for each of those models from the cross-validation. And we can see here that the multiple linear regression performed pretty well at 20.9. Getting rid of the RH feature and performing that feature selection actually did not improve the mean squared error score. And remember, here we're looking for a reduced mean squared error. And then finally, the log actually did perform the best, the log transformation, by reducing it by about 0.23 units. So we ended up evaluating that the log transformation on the multilinear model would be best. And then we got we tested that on the validation set, on the test set, and we got a final mean squared error of 20.08. So this is pretty great. Remember that this is the average square difference between the predicted and actual. And if we take the square root of around 20, that's about 4.5. And within the 75.5 range of the target values, that's pretty good. That's about 0.05% of the range. So I would say that the model performs pretty well.